So, what we're talking about today is called theoretical probability. So, basically, like, this is when someone says, in theory, you would get this. So, theoretical is like if the actual statistics were always true, which is, we know, is not the case. You know that you can flip a coin once and get heads, and then flip a coin again and get heads. Um, but theoretically, it's like you would get heads and then tails and then heads and then tails every time. So we know that the theoretical is not always exactly what happens. So let's define it. Theoretical probability is what should happen in an experiment. Um, so basically, like, kind of like my example, but maybe like if you toss a coin 100 times, 50 of those would be heads and 50 of those would be tails. So, like, example, 100 times. We toss a coin 100 times, 50 are heads, 50 are tails. Experimental probability just means what actually happens in an experiment. So this would be, I actually get a coin and I flip it 100 times and I basically tally every time I get heads or tails. So it's what actually happens. Um, so this is going to be a little bit more complicated for the students that are at home, but maybe you can find someone in your house that will play rock, paper, scissors with you. If not, I can just give you some like big numbers. Um, so in theory, complete the table below showing who would win the game under different circumstances. Um, if you do rock and rock, nobody wins. If you do rock, if player B does rock and player A does paper, player A wins. If player B does rock and player A does scissors, then player B wins because scissors beats rock. Paper and rock, player B wins. Nobody wins. Player A wins. Scissors and rock, the rock would be the scissors, so A. Paper, scissors beats paper, so that would be B, and then nobody wins if they do the same thing. So, thinking about the theoretical probability of this, there are 9 different possible combinations. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 different possible combinations. So our denominator is 9. There's 9. The sample space has 9 different options. So denominator is 9. What is the probability of player A winning? So if we look at this, player A wins 3 out of 9 times, which is a third, which is about 33%. The probability that player B wins, there's 3 Bs, so again, 1/3, 3/9, 1/3, which is another 33%. And the probability that it's a tie is these other 3, and that's also a third, so 33%. So theoretically, a third of the time, somebody, like player A would win, player B would win, or there'd be a tie. If you can play with somebody else, it says play 25 trials. In class, we're going to do rock, paper, scissors together and play it 25 times. If you're able to play with somebody, go ahead and try to do that now. If you can't play with somebody, let's just go with 9, 7, and 9. That's my like notes page has that information. So we're just going to make that up. So let's say you play 25 rounds, player A wins 9 times, player B wins 9 times, and there's 9 times that there's a tie. So there's a total of 25. So here there was a denominator of 9. This time there's a denominator of 25. So if you play with somebody, obviously these numbers are going to be different. What percent of the trials did partner A win? 9 out of 25. That is about 36%. What percentage of the trial did partner B win? That would be 7 out of 25, which is about 28%. And then a tie is also 9 out of 25, which is another 36%. So does this still add to 100%? Yes, it does. Does this add to 100%? Well, technically, those 33s would make 99, but we know that this is a repeating decimal. So yes, they all add up to 1. A third and a third and a third makes 1. And 9, 7, and 9 add to 25. So this makes a whole, but we can see that when we actually do the trial, we do this experiment, the experimental probability does not always turn out as nicely as a theoretical probability with this nice, neat math. So, do the theoretical results match the experimental results? And this is no. Um, so basically, we would expect 33%. So basically, player A wins and ties happened more often in the experiment than we predicted from the theory. How could the experimental results get closer to the theoretical results? So basically, the best way to get the experimental results to be closer to the theoretical results is to do more trials. Um, Basically, the more trials you do, so instead of doing 25, maybe you did 100 rounds of rock paper scissors, but the more trials you do, you'll have results that are closer to the theoretical results technically, because there's more options for it to kind of even out and be similar. On the back, so 9 and 10 are all using this spinner. The table shows the result of rolling a die. Oh, no. This is rolling a die. This spinner goes with number 10. Sorry, my bad. The table shows the results of rolling a standard die 50 times. So the standard die has 6 sides. If we think about it, the theoretical probability of rolling a 4, there are 6 sides, and only one side is a 4. So 1/6 is the theoretical. In theory, the math would tell me 1/6. Calculator. 1/6 as 8% is 16.6 repeating percent. What is the experimental probability of rolling a 4? So here's a 4, and they rolled it 5 times out of 50, which is 1/10. And 1/10 is 10%. Then it says, compare this to the theoretical. This is lower than expected. And the directions don't say you have to convert this to a percent, but I find that if you convert it to a percent, it's easier to compare these numbers, because sometimes when we're comparing a fraction to a fraction, it can be difficult to understand the comparison. So I like to see the percent because I feel like the percent helps me compare them. So in our experiment, we got the 4 fewer times than what the theoretical probability would tell us. Shaded letter, the theoretical probability of a shaded letter. So 1, 2, 3, 4, 5, 6. There's 6 shaded, and there's 8 total, which is basically 3/4, which is 75%. So we would expect 75% of the time we would land on a shaded letter. What is the experimental probability of spinning a shaded letter? So A, B, and C are shaded, and E, F, G are shaded. They spun the spinner 75 times. So I need to add these numbers because all of these are the times they landed on a shaded. D is not shaded and H is not shaded, so we can't include those. So 5, 12, 10, 11, 13, 9, 60. 60 out of 75 is 0.8, which is 80%. So in this experiment, they landed on a shaded letter more frequently than expected. We expected it to be 75% of the time, but according to their experiment, it happened 80% of the time. So this happened more frequently. All right, using samples to predict. The table shows the result of tossing a coin 100 times. So we're going to use a sample to predict. So basically, how many heads would you expect to occur in 300 tosses? Well, 1 out of every 2 would be a heads. But how many out of 300 should be heads? If this is the probability of getting heads, what if we scale that up to 300? Let's scale this up to 300. And you can think of this as a proportion, or you can mathematically think half of this is 150. So theoretically, we would think if you flipped a coin 100 times or 300 times, 150 times you should get heads. Now this says, based on the experiment, how many heads would you expect to get if you did 300 tosses? So this is 100 tosses. So out of 100 tosses, they got 58 heads. But what if we did this 300 times? And this makes me think of a scale up, scale down. So to get to 300, I would multiply by 3. So 58 times 3, whoops, that's 9 up. Is 174 because I multiplied by 3 to scale it up. Okay, so we're thinking about the probability as a ratio and a proportion, and we're scaling up that proportion. Number 12. The table below shows the random results of randomly selecting a letter from the word rhombus 80 times. Okay, rhombus has 1, 2, 3, 4, 5, 6, 7 letters. If a letter is randomly selected 500 times, how many vowels would you get? I'm actually going to make this a straight line. Vowels would be O and U, so 2 out of 7. And we make this 500 times. For this one, I might want to cross multiply and divide. Letter. Cross multiply. Right? 7x equals 1,000. Right? 2 times 500, 1,000. I'm going to divide by 7. With this decimal, let's just go ahead and round it. So 143, about 143 times. Now, based on the experiment, we're going to do the same thing. So the experiment was done 80 times. Eval was landed on 24 times. 6 plus 18 is 24. We're going to scale this to 500. And again, right, cross multiplying. Boom. 80x equals 24 times 500. 12,000. And then we're going to divide by 80. With this experiment, we would expect it to happen. Wow, I don't know why it keeps doing that. We would expect it to land on there 150 times. These are pretty similar numbers. Okay. So there's a digital activity. People at home, you don't have this paper, you'll be able to complete it online. The homework. So with the homework, you're going to do 1 through 8. 1, 2, 3, and 4 are all talking about the same spinner. So the first 3 questions are the simple probability. I don't want the decimal, I want the simplified fraction and the percent. Only the simplified fraction and the percent. So first you do theoretical. These 3 are theoretical. Then on these 3, you're looking at this table, which has the tallies. Okay, so they landed on 1 6 times. They landed on 2 4 times. They landed on 3 7 times. So 2, these parts talk about the experimental probability. And then it says compare to the theoretical. Was it more frequent or less frequent in the experiment? And then 3 and 4 are those scale up. So these are ones where you're going to use a proportion. And 3 and 4 is talking about this, and you're going to use a proportion. So remember, it says theoretically and based on the experiment. Okay? So theoretically is talking about mathematically what would happen, and then based on the experiment is talking about what you see in this table. You're going to do 5, 6, 7, 8. 5, 6, 7, and 8. With 5, 6, 7, 8, they are all talking about this spinner that's here with number 5. The number 5, the 3 parts are talking about theoretical. Number 6, these 3 parts are talking about the experiment that was done 50 times. Remember, it says compare to the theoretical. So tell me, is it higher? Is it lower? Is it what you expected? And then 7 and 8 are this based on scaling up and scaling down based on the theory and based on the experiment. You don't have to do 9, 10, 11, 12. That talks about cards, and we're not really familiar with cards, so you don't have to do 9, 10, 11, 12. So 1 through 8 on the homework.